Thin layer chromatography. Yeah, that's what we're getting ready to discuss in this video. So chromatography, you're probably taking this class in conjunction with our second instrumentation course, and our second instrumentation course focuses on chromatography. So this word is not new to you, but if you're not taking our instrumentation course, then it might be. So I at least want to take a few minutes and go over some basic definitions of the world of chromatography and talk about how that relates to amino acids and their separation. So chromatography is the old word that meant color separating or color rotting. And the reason that we still use chroma is because we've never really changed it. One of the first kind of chromographic techniques was done on plants, and those were chlorophyll based, and these are colors that we actually saw, and we saw colors being separated out, and hence the word chroma got into the mix, and it just kind of stuck around because we liked the way that it sounded. However, today we do not have to rely on things being colored in order to separate. Separation can happen, and then we can use chemical reactivities to make these things colored if we want to see them with the human eye, or we can use an instrument that can see things that we can't, and they will be able to pick up maybe some of the invisible dots that we can't see on a sheet of paper. So no longer is really chroma or color necessary for these techniques. So chromatography, that's what that means. It's just a fancy word now that means separating. That's all that it is. And this is separating by something with a thin layer. And thin layer is really referring to a sheet of paper or a plate with silica or alumina on it. Okay, so think of a microscope slide, and on this microscope slide, you kind of have a layer of silica, a white powdery substance on the front of this microscope slide. Or alumina, which is also a white powdery substance on the microscope slide. So you've got this kind of layer of very fine dust that has been attached to the glass and has been baked for you. So that means you will take this slide, and what happens is that you will spot, what we call spotting, your sample on it. So down here at the bottom, I'm going to take a TLC slide, so here we go, and with a pencil, what I would do is that I would draw kind of a dotted line there. And this will give me kind of my point of origin. That gives me basically the starting point where I need to put my sample that I'm using. So I'm going to spot my sample right here on the start line. And then when I do that, and I can spot it a number of different ways, I use a capillary tube, just kind of dip it down into solution, and then just barely dab that onto the TLC plate. I could use one of those glass Pasteur pipettes, so I could take one of those glass pipettes, dip it in solution, put one little drop or two little drops on the TLC plate and let it dry. But that's how I would load my sample up. And then I would take this TLC plate and I would put it in a beaker. And this beaker will have what we call mobile phase in it. So a liquid solution that this plate will kind of sit in, and this is what we call mobile phase. And just like a straw, this TLC plate with the silica or the alumina or just the sheet of paper that's been cut out will begin to suck up the mobile phase through capillary action. So just imagine you putting a straw down into the beaker and sucking up with your mouth. So the plate will do the same type of thing. It's doing the sucking. So the mobile phase is basically being sucked up the TLC plate or the piece of filter paper, and the mobile phase begins to mix with the sample that you've spotted. So that's what we call the mobile phase. The alumina or the silica, so silica, alumina, or the paper. And when we talk about paper, it's really cellulose that we're talking about there. That is called the stationary phase because that's not really moving, right? That's on the microscope slide, or that is the sheet of paper. That's not moving. It's not going anywhere, so we call that stationary phase. So mobile phase is getting sucked up, and the stationary phase is kind of there as a foundation in a way to give these amino acids some traction so that they can begin to move. Okay, so what happens is that over a course of time, we see this mobile phase being sucked up the plate. So what I'm going to do is I'm going to draw an arrow, and the arrow will be right here. And we will see mobile phase going up, 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 up the TLC plate. And then we know that the TLC plate has finally developed because we can see the solvent line. And the solvent line might approach up near the top. That's preferably where we would like to see it. And we would pull out the TLC plate at this moment in time. So the solvent line, once it approaches the top of the TLC plate, you will then grab the TLC plate and remove it from the beaker that has this mobile phase in it. So the reason that we do that is if the solvent line goes over the TLC plate, the solvent line distance is very important. How far the solvent line actually traveled up the plate, that's something that I need to measure. And if I do not catch it before it travels the top of the plate, then I can't really do my measurements. And if I can't do my measurements, well, the separation was no good. I need to completely start all over because I can't provide you any numbers. So that's the number one priority. Take a look at your solvent line, keep an eye on the TLC plate, make sure that the solvent line doesn't go over the TLC plate, and remove it before it reaches the top. So about 1 centimeter from the top is kind of where you want it. Over a course of time, what begins to happen is, let's say that this sample is a mixture of different ones. And this sample, this spot, begins to travel up, 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 up. So what begins to happen is that we begin to see some separation that happens on the plate itself. And let's say that there's 4 amino acids that are in that sample that I spotted in the very beginning. What we would hope to see are maybe 4 different dots, one representing each amino acid that is there. So again, you got to kind of know something about your sample, how many, or what's the idea of how many amino acids that I should be looking for. If there's 5 amino acids in the sample, you would see 5 dots. If there's 2 amino acids in the sample, you will see 2 dots. If there's 1 amino acid in the sample, you will see only 1 dot. So it really depends on how complicated the sample is, but each dot represents basically an amino acid. So dots equal amino acid. These dots you will not be able to see. So typically what will happen is just like before on the electrophoresis paper or chamber, you would have to use some type of indicator. So an indicator is typically used, and that makes it change color. And what we would see is if we used anhydrine, these spots would turn purple or maybe yellow depending on what amino acids that we have, or maybe proteins that we have. But they would tend to turn purple, and then we could visualize those dots and see basically where they went, how far did they travel, and so forth. Okay, so what's the story here? How does the separation happen? Well, the separation happens based on polarity. Okay, so polarity, you need to look at the amino acid polarities. The most polar amino acids that we have, the most polar ones, are those with charged side chains. And if I take a look at the amino acid list, well, there's a couple of those that have charged side chains. We'll list those here in a minute. The next most polar are those that can form hydrogen bonds. So here we're going to put charged R groups. So this is the most polar. What will come in next are the ones that have side chains that can form hydrogen bonds. All right? And then what would come next would be the amino acids that have the hydrocarbon side chains. So, we kind of broke these down into groups and families, right? So if I take a look at alanine, alanine had a CH3 group as the R group. That is a hydrocarbon. And that was classified as basically aliphatic, which means nonpolar in a way. Fatty-like, right? Okay, so this alanine would fall under the category of number 3. It is a hydrocarbon. So this is not polar at all. So hydrocarbons, I'm going to put in parentheses here just so you remember what we're doing and what we're ranking, non-polar. Okay, if I had serine, serine had a CH2OH group on it, CH2OH. It wasn't a full charge, but that group, an OH group, can participate in hydrogen bonds. So serine is more polar than alanine is. And then if we take a look at some of these acidic or basic groups, the most polar ones, well, this could be something like maybe glutamic acid. So glutamic acid. I'm not going to draw the R group there. You can go back and look at it, but that glutamic acid, well, it's got a C double bond OOH, and at physiological pH, it's fully blown negative. So this is a fully polar charged molecule because of that. So that's the first thing that you've got to do when you look at TLC and try to figure out, well, why did these things move the distances that they did? You've got to rank polarity first. Electronegativity will also help you out with this. So what we show is that in a TLC chamber, well, we've got a mobile phase typically, and the mobile phase is for the most part non-polar. And then we have a TLC plate, and the TLC plate typically is the polar piece of this whole puzzle. So what begins to happen is that if this setup is chosen, well, the mobile phase is being sucked up through the plate. The plate is polar. So the polar amino acids are attracted to the plate more. And the nonpolar amino acids stay in the mobile phase more. That means they move further up the plate. Okay, so if we had a TLC chamber, and this is the setup that we used, a nonpolar mobile phase. Well, the spot that's down here at the bottom, this would be your more polar amino acid because it has an attraction to the paper. It likes to hang out with the paper, and it doesn't really want to move with the mobile phase because it doesn't have anything in common with it. Well, if we take a look at the top spot, we would see that this spot has moved the most. And because that's moved further up, it means it likes to hang out with the mobile phase more. If it hangs out with the mobile phase more in this setup, then this would be our more non-polar amino acid. So that is how you determine the order of separation, or at least predict the order of separation. And this is using a non-polar mobile phase. Now, what if I didn't use a non-polar mobile phase? What if I used a polar mobile phase? Well, everything goes backwards then. So if I use a polar mobile phase, well, the more polar amino acid likes to hang out with the more polar mobile phase, and it travels the farthest. So that is how we kind of determine the order of amino acids, and you need to look at the mobile phase and figure out first what type of mobile phase you're using, and then you can go from there to answer the question.